So recordings are available online. Good idea. Which folder is that?
So I am recording, so it's on YouTube. So if you search for my name on YouTube, I need to send that on Canvas. But good thing about having a weird name is that I'm unique as far as I can tell. So if you know how to type my first and last name in, it's me. And you find me online, there's no mistake, it's me. Whatever, if it's good or bad, it's me. I can't claim it's somebody else. So if you just search for my channel on YouTube, I've been recording this course since 2015, so you can actually go back. The only problem is that Python part started in fall, so only last fall and this spring apply to this version of the course. Anyway, so let's keep going with so we started working with Numpy and basically creating arrays. They're a little larger than whatever it is that we could type in. So then the problem comes in, hey, I have a large array. How do I see what it is? Again, humans are not good at parsing data and large amounts of data. And as engineers, we need to look at the data that comes in and say, what's wrong? Or is anything wrong? Or how can I use this data as something else? So we have to learn how to visualize data in some form that is more effective than just looking at the table of numbers. That ain't good. Okay? And plotting, first thing is just plotting the data. Now we can think about data as just data, or data as functions. Sometimes we kind of have both. We often like functions, and by function I mean functional relationship is, if I have function f, you give me an x. For the domain of that function, I can give you a unique y that is f of x. If I have two possibilities for f of x, it's not a function. I have two different functions. Okay? Now, we often like having a functional relationship, A, just to play in calculus, because that's fun in its own. Okay? But B, actually, because if I know that something behaves in a certain way, maybe I know that from a physical law, and maybe I know that because I measure the data. Either way, I can try to predict. And prediction is part of engineering design. So in that sense, we want to be able. So first thing that we wanted to do is just do a quick or simple plot of things. So last time we used some Numpy functions to actually create. So I'm just going to recreate something similar that we did from last time. So who can tell me how can I create an array of 200 points that are in between 4 and 5? So you're saying x is np.linspace, and then between 4 and 5, 200 points. Okay, so this is a built-in function, so it already exists. We'll simply use it. If you don't know how to use it, then you search in either, you can do help in any kind of Python environment, or really what's going to be much better readable and presentable, you fire up your favorite search engine and look for linspace in Numpy, and you will get how it's used. So this function has 3 inputs, and down the road, our next assignment, soon enough, we'll be creating our own functions that do what we want them to do. So these are 3 inputs, and they have to typically be in certain order. For this function, first one is interpreted as the starting point, then ending point, and how many points do I want in between. And linspace is going to give them equal spacing. Okay, great. And then beauty, and I can print this array if I wanted to actually look at it. I'm not going to do that right now. And then if I want to do some function of it, I don't know, I'm just going to here do x squared minus 4 times x plus 7. I have no idea. I'm just coming up with things. Okay. Let's see if this works. Okay. So what I think this should do is that I would like it to take, this is an array, it's a one-dimensional array. I would like it to create an array of the same size, okay? And every element of the array is the square of the corresponding element in X minus 4 times corresponding element in X plus 7. So it's going to do precisely the same operation of every element of array of X, or so I hope. Let's see. And typically, if it goes without complaints, I did something about that is according to the rules. Okay? And now the next part of it would be to plot it. So what did we say we need for plotting? So what did we say we need to for plotting? First thing I actually needed is import Numpy as NP. But since I had this notebook running, that was already imported from our last class. But generally, it's just a good idea to throw it in. But there's another module within Python that I need to import in order to plot. Which module is that? I will call it PLT as PLT, but its full first and last name is matplotlib. So this is not to say that you cannot use something else. There's actually a zillion of plotting options out there that you could use, but this is one that is right now the most typical for two-dimensional graphs. And since it serves our purpose, there's no need to change it. Change it if you need to. And now that I have that, then this family that I'm now calling PLT, this family can just simply plot. And the simplest way, just the first thing, is to plot X and Y. And the key in any plotting function that does the graph is to have arrays of points you want to plot, and those arrays have to be of same dimensions or same number of elements. So it's going to understand this if there is 200 in each of these arrays X and Y. It's going to understand the corresponding elements, so X of 0 and Y of 0, X of 1 and Y of 1, and keep going to X of 199 and Y of 199, because that will make it 200. That's going to be understood as 200 separate points to plot. And plotting software, it needs actual points. Even though once we plot it, it's going to look like smooth and continuous and there's everything in between. But what it's really doing, it's kind of interpolating in between with a linear function when it's plotting. But if I have enough of them, it's going to look good. Okay? So let's try. Okay? So this should be a parabolic function, but I took just a random function, so it's almost linear on the segment 4, 5 that I picked. It doesn't matter. If I actually wanted to see individual plots, I can actually tell MATLAB different selection, and I can describe point markers, I can describe lines in between, and colors. And based on what I type in whatever order, it's going to figure out what it is. So if I wanted this to be red, and circle, and connected with dashed line, I would write this down. And in your slides, you have a table that has it all. And again, I have so many, I have 200 points that I can barely see differences between these circles. However, beauty of the code is you can quickly change it on the fly. If I change this to 20 and re-execute, I'm going to actually see these individual 20 points. So as smooth as plots might look like, they're all discretized underneath, and they're showing certain. As smooth as this, what is my screen, and has even these beautiful pictures down here, as smooth as it looks like, it's very well pixelized, and you can see individual points. But there are so many of them, which we call resolution, that this picture looks smooth. In your cameras, on your phone, and otherwise, they're getting better and better in terms of increasing resolution, which gives appearance of continuity. However, computer world is discretized. Great. So this is just a brief review. And then we can dress this up in all kinds of ways. I could add a label if I had multiple points. And I'm just going to say, I'm going to be goofy and say hello. So I'm going to plot my function as hello, or hello quadratic function. And I'm going to say PLT legend. And that's actually going to tell me that, hey, this line has this goofy name or label. And this is specifically helpful if I have multiple lines. You can have a figure and you can describe in text under figure that, oh, your red curve is this and your blue curve is that. But this actually makes it really quickly visible what it is. And you can add anything to it. So I could technically say x and 2 times y. How's that? And I'm going to put that in, let's see if magenta works. And I'm going to put little diamonds in mine. I'm going to copy here. So this is my quick fabrication of the second data set. It's just simply multiplying the first one. Oh, and I have nobody saying anything about my oh, so now I have 2 of them. Okay, and D is for diamonds. So the point is, if you can think of it in terms of changing the color, changing the markers, and all that, you can do it. Question is, how complicated do you want it to be? And just having a set of 5 or so colors that you know, and 3 or 4 line types like dashed or solid, and 5 or so markers does it. Like that does the trick most of the time. The most important thing is to label your plots when you're presenting them. And here my x and y don't mean much, but I could put PLT x label to give this axis a name and y label to give y label a name. Great. Again, you can modify. In the Lecture 2.4 script that's a notebook script that I posted for you in class, you can actually see a very kind of advanced way how you can manipulate font sizes to be precisely what you want it to be. Again, that's for your information, just to show that you can manipulate things to the level of detail you want to. For most cases, this font size that basically Python picked for us is actually okay. You do want to, whatever you show to in a PowerPoint or so, you always want to have font size that is large enough for people in the room to read. If not, they're not going to listen to you. Whatever it is that you're presenting, they're going to be squinting trying to read. And we can't fight that as humans. So they're going to completely disregard what you're saying, and they're going to be like, what is that plot size? So you don't want that. You always want to have font size that is large enough. Okay, now we're going to do one more trick before we actually move on to 3D plots. And that is actually putting comparison of 2 plots, one above each other. So basically doing subplots. So you can do as many subplots as you want. That's typically done for comparison of the data. Sort of like you can kind of see eye to eye. You might want to, if you have certain type of functions, you might want to show them on the same plot, which is what I just did. That's the most useful. But here and there, you have maybe too much data, or you have 2 different types of data. So if you're showing porosity logs, for instance, bell logs, you're going to have porosity log and permeability log. Those are 2 different sets of numbers, right? So you will have them next to each other. That's basically put next to each other. So I'm going to tell you how to do that here in Python. So let's do subplot example. So now I'm going to figure out 2 different types of data. I'm going to import Numpy as NP again, even though it's already imported, just to practice that that's what we need to have. So I'm just re-imported both modules just to remember that I need them. And I'm going to figure out two types of data. They're going to be sort of like a sine signal and a damped sine or signal. So I'm going to put my x1 as also lin space between 0 and 5. And I'm going to leave it at a default. So if I don't enter the third number, which is designating how many points, it's going to give me a default. Let's see how that works. So what I'm also pointing here is that this function that is built in a pretty smart way. So it can accept different type of inputs. And based on different type of inputs, like I can put 2 of them, I can put 3 of them, I can possibly put more, it's going to interpret things differently and adapt, which is a very nice way to program. It has official name of function overloading. And my second function is the cosine, but not just cosine of x1. It's going to be cosine of 2 times p. And remember that constant p or pi is np dot pi times x1 and times np exponential of minus x1. So it's a little more complicated just for kicks. So I have also introduced another built-in mathematical function, which is exponential. It works just like you would expect it to work. It's e to something. And then I'm going to have, this is my data for figure 1 and data for figure 2. It's going to be slightly different range. And this also, that's why it requires a separate plot. On the same plot, it would probably look a little odd. And this is going to be just cosine of 2 times so essentially, first one is a cosine function that is damped with an exponential decay. And the second one is just a cosine function.
So the semicolon, it doesn't do anything to
The semi?
I don't know what it's called in English. The dot with the colon.
Yeah, the semicolon is full,
Semicolon. This one? Oh, this is my, it doesn't do anything. This is my habit.
From MATLAB, right? Because on MATLAB.
From MATLAB, if you don't put it in, then it's going to print this entire array out.
Right.
So I'm by now trained to put it in. There are some languages that require, like C, you have to put it in. And in Python, you have to put it in this case. So if I just wanted to do this, both 2 commands in one, let's do that just for fun. Then you have to separate them with semicolon. Great question. Okay, so I have the data. Now I actually want to plot it. Now normally what I would do, I would really just say plt plot x1, y1, and I don't know, circles connected with a line. So that would be my regular plot, but then I would just have one plot. Now I'm going to tell it, no, create a subplot. And I want to have 2 subplots because I have 2 sets of data. Okay? So I'm going to say plt subplot. And I'm going to tell it, hey, you have 2 subplots. And the one that I want to plot is in position 1, 1. Really like a array. And then my next subplot will be in position 1, 2. And the difference between 1, 1, 1, 2, and 1, 1, 2, 1 is just like in matrix. Do you want them in the same row or in the same column? Okay? And of course, you could have 4, so you could keep going. I'm not going to complicate that much. Right? So I could tell it, hey, I'm gonna have 4 here, and then have a position 1, 1, 1, 2, 2, 1, and 2, 2. Okay, and compare 4 of them. But let's just look how this looks in the most simple way. And I don't know, diamonds, sure, diamonds. And it doesn't like something.
You're going to plot instead of PLT.
Typos.
What was the problem?
I put in plot instead of PLT.
Oh,
And luckily somebody here has better vision than me, so they immediately spotted what I did.
oh, that's right.
Right.
You got
So this is just 2 very simple plots. Everything that I didn't specify went as a default, but I can dress it up, okay? Let's dress it up. So I'm gonna give this PLT Y label. I'm gonna call this one's the damped function. And the bottom one, X label, is undamped. Oh, not X label, Y label. Debug on the spot. So this is my undamped sign, and this is my damped sign signal, right? This is a signal processing 101. Signals could be damped and undamped. Okay. So in damping, my amplitude keeps going lower. Now, what else do I want? I want to possibly put here X label. Since I don't really know what this is, I'm just going to call it X. So that shows up here. Presumably this is X as well, so I don't need an X label in the top plot. Again, I can now do all kinds of things. If I put a title, title is way better to put on the top plot, so I can put title saying comparison of signals. Here we go, comparison of signals. You can keep going and dressing it up. The key point is the way I told Python, hey, throw one of these plots to the subplot. I have to tell it how many subplot and what the arrangement is. And by the way, if you don't plot anything, this is just a, let's see what happens if I just comment. So subplot function will just create a default plot, and it's going to sit there waiting for some data. Okay? So this is sort of a default object, a plot object, and sort of a space for any kind of plotting, and then you keep adding to that object by these commands. So you should understand that
What does damped mean?
my amplitude keeps decreasing. I'm damping my signal, means that my amplitude of the signal keeps going down. Strength or amplitude of a lot of things will damp as they pass through different media. Ningyu will tell you that magnetic field from the source will decrease, from a point source will decrease 1/cube of the distance. Okay. Attractive gravitational force decreases with the square of the distance, right? So the strength of it decreases. So a lot of things, they kind of deteriorate with time or distance due to whatever is going on physically. Sources could be various. Okay? All right. This is basics of what we need. Again, I want you to just have the agency to plot your data. the key is to have the data. Here we learned how to artificially create some data using functions that are built in. But you will sometimes simply have the data that you will read in. And we will learn in our next endeavors, we're going to learn how to read in the data from a file. Okay? So there could be various sources. Now I would like to move on to 3D plotting. And I'm going to go back to my PowerPoint. So before we have 3D plotting, let me just show this slide. So this is in your slides. You can search for this information online as well. So this is basically all the typical choices for colors that are already built in with the little letter codes, B, G, R, C, M, Y, K, and W. Don't plot white on white, nothing will show up. If you want to plot white, you've got to change the background color to something else. Okay? Just an FYI. And you can change that background color, quite frankly. I don't know how to do it, but I know it can be done. So if I need to, I'm going to search. Do beware that it's actually for vision, and I have vision problems. The best is white background with some black or strong color on top for just seeing the differences. All other colors might not work as well as you think they do in a larger room where you're projecting. So there's solid line styles. I explained dotted, or I use dotted and solid, but you can do dashed and dashed dot. And then this is just a partial list of possible markers. I use X's, diamonds, D, and circles. There's all kinds of triangles. You can put pentagons, stars, hexagons, you name it. Okay? So you can play with that. As long as it's clear what you're plotting and you differentiate plots that you need to differentiate, you're going to be fine. Okay? And then we learned how to do multiple lines in the same graph as well as multiple plots within one figure. One thing that I did not specify here, this is optional. This plt.show, sometimes because we are working through the web browser, sometimes as if you need to push the memory out to that web browser to kind of refresh things, quite literally. If something appears stuck or not plot the way you asked it to, then this plt.show is going to push it or refresh it. So it's optional here and there. If your browser is not communicating properly, you need to do that. Okay. Or if you make a change and that change doesn't appear to take effect, then plt.show is a good idea to do. I'm not going to go through histogram, but you have this example in your both slides, but this is just how to create a bunch of data, in this case just a distribution of drawn from the random distribution, normally actually from normal distribution, and basically then just plot a histogram of something and normalize it as a probability. Again, you can dress it up, change colors, and there's here even an interesting way. Hey, I'm going to do symbols. So there is a way. We're not going to focus on it here. I just want you to know there's a way to get symbols such as Greek letters. And it looks like a little bit of programming. You have to tell it, hey, this is a formula, mathematical formula, so it's going to interpret those as special type of symbols. So there is a way to get the symbol mu and sigma in the text. And also there's a way to add text in certain locations. So this is the location in the graph, and this is the text we're adding. Okay, so let's now just do a quick assignment to review. I'd like you to create 100 points, X and Y, that are on a circle of radius 1. So this will go back to wherever you learned geometry and how to create points on a circle. If you can remember parametrization of a circle, that'd be great. So you can create these points. And I want you to plot that circle in red color and solid line. and then find online how to change that line. Look at me. To a thicker line. I projected the solution for a moment. So, okay, plot a red circle. So I'm gonna work in. Where's my? All right. So I'm gonna plot it here. Plot. Create 100 points x, y on a circle. Plot circle in red line, red solid line. Something like this. Whatever it is that you're plotting, this is the key. Now, question is, how do I fill in what I'm plotting? How do we parameterize a circle? Half of it, yeah, so now half the bottom half. That's fine. Bottom half is the negative of the What did your trigonometry class tell you that circle is? That's not trigonometry, that's regular geometry. It's parameterized by theta here. Ah, that's the fastest way anyway. You can do the x squared part, but then you're gonna plot top part and bottom part separately, which is doable. So x is sine of theta, y is cosine theta, or the other way around. This? What is this? What is this? Aye.
That's why and that's other way.
This is sine, this is cosine, right? And then indeed, sine squared theta plus cosine squared theta is 1, which is y squared plus x squared. Yes? That's trigonometry class, I believe. All right, so what do we do here then? First, I need theta. So I'm going to do from 0 to 2 pi. How many did I say? 100. Red solid. Looks like an egg because my axes are not same. I will let you find out how to do this line to be double, as well as how to make this egg proportional. So basically, I need a command that will make these two axes the same length. Right now, it's not. This one, 0, 1, is shorter than this one. And I also want you to modify the axis, which is something that we did last time, strictly to -1, 1 in both dimensions. So your assignment is axis, set axis to -1, 1 times -1, 1. Figure out how to do a thicker line width 2, and make axes proportional. Same length. Okay. And then you will create a little quiz thing for you to submit this code. Just this piece, you can just literally do text, or you can output this as a separate file. Either way, what's the easiest for you? Python or IPY?
Anything but not IPY.
Okay, so he doesn't like IPYNB, so output this piece of code, copy it in the new file and export it here, file, save as, download as Python. Okay? Or HTML or anything else, apparently. Don't do LaTeX. It's okay.
Can you scroll down on that?
Yeah.
Actually, PDF would be the easiest, eh?
It will be complicated for them, so maybe HTML is the easiest.
Okay. So either HTML or Python or one of the two.
Can you scroll up, please? No, right there.
So set axis to -1, 1, figure out how to do a thicker line, and make axis proportional. So that's a little assignment, search assignment.
That's an in-class assignment, or you have to do?
You're gonna have to do it and submit by tonight sometime. Let's do 11 p.m. Can be tomorrow, 8 a.m. That works.
I've got 2 tests tomorrow.
When is your test?
9 a.m.
Actually, let's just do it by next class. I don't care. By Friday class, 11 a.m. I just want you to do it. So,
I've got a 9 a.m. test. And then
woohoo.
7:30 p.m. test tomorrow.
Tomorrow's a big day.
Yeah.
All right, let's move on. So again, you can control font sizes. This is if you're really going into micromanagement. this is just a general way to control and really say, hey, for both fonts and axes and ticks on the axis and on x-axis, y-axis, legend, figure, you can control it all, okay? All I want you to take away from this size is you can control anything that is output on that plot if you want to. Most of the time, there will be certain default choices made for you, and most of the time, those choices work. For the case that don't, you have to go into micromanagement of all of these, okay? So this is just an example. There's another hack is to, sometimes you have to, there's a figure that is produced, has certain size, you can control that, and then you can try to enlarge whatever is plotted relative to that figure. That's just another way to increase the font size of your, if you want to have fun with it, go. I'm not going to test you or anything like this. This is just a little bit of extra information. Okay? Now let's move on to 3D plots. What happens if I actually have a 3D plot like this? Right? How do I actually plot it? In this particular case, this is actually a plot of the function z of xy that is minus x times e to the minus x squared plus minus y squared. Okay? So this is just a function, just some function that depends on two variables, x and y, and I want to plot it on, this is a three-dimensional plot, right, because it's a surface. Now, again, just like in 2 dimensions, I have to have all of the points, and I have to create all of the points. What it means in this case, and I already have a grid that suggests that, is that I literally have to have, let me walk around this plot, this point, this point, this point, this point, this point, this point, and so forth all the way down. And then this point, this point, this point, this point, and keep going. And so an entire array of locations. And in each location, it's a three-dimensional point. So in each location, I have x, y, and z determined. That is, so there's x and y in x and y, and then there's certain height to it in z direction. Okay? So I need a grid of points like that. So matrices are an ideal way to actually parameterize that. So basically, first thing first, I need a grid of x and y points, okay? And that grid is two-dimensional, and each point on the grid has both x and y dimension. Do we agree? So that's basically this. In this simplest case, let's just walk down this grid that is plotted on the bottom. It's a grid of these points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All these points that I'm pointing at. So this point has x minus 2 and y minus 2. This point has x minus 1 and y minus 2.
We can't see
We're
the.
gonna see what you're pointing at.
Oh, it's not moving? Okay, well, figures. Minus 2 minus 2, minus 1 minus 2, 0 minus 2, 1 minus 2, 2 minus 2. Do we agree? Next line. Basically, my x's are repeated. Minus 2, but now I have y minus 1. So minus 2 minus 1, minus 2, minus 1 minus 1, 0 minus 1, 1 minus 1, 2 minus 1. Then again, x's are repeated, and my y's are 0. So minus 2, 0, minus 1, 0, 0, 0, 1, 0, 2, 0, and so forth. But I decided to go row by row. I could have gone column by column. In the columns, I would notice that my y's are repeated and my x stays the same. So it's minus 2, minus 2, minus 2, minus 1, minus 2, 0, minus 2. So see a pattern to it. So I have to create myself a grid of x and y's that do that. And then I need to compute z's for every x and y couple. Okay? Great. So essentially what I have is I have a matrix X that has these x's, right? So x coordinates of all of the points, and a matrix Y that has corresponding y coordinates. And then I know if somebody gave me those x's and y's, I can easily compute Z based on that formula using, if they're NP arrays, I can compute with the entire array. Great. Yes? Everybody follow? Let's do that. Okay? So basically, in any kind of, the point is that I have to have those x and y's, compute z's, and then just plot them. And I have functions that are plotting them already. So let's go back to my notebook. And I'm going to say, I'm going to actually open a new one. So I'm going to call this Lecture 2.5 Spring 2019. Okay, so these are my 3D plots. So I'm just going to say, hey, x is, let's say that, what do I want to plot? I can create any x's. So these were -2 to 2, right? So NP linspace of -2 to 2 and 5 points. Let's just print these to see that I got what I wanted to get. Ah, what did I? -2 points, Dr. Pradanovic, on your test. You didn't do import Numpy. So this is my x's. These are my x's. And I'm going to do the same for my y's. So both of my x and y's, this is the range that I want to have for them. Okay? Now the question is, how do I get those matrices? Technically, I could go and create them. Basically, X matrix had sort of rows repeated and the other one had columns repeated. I could figure out how to do that. But there is actually a built-in function that's going to give me those. And I'm just going to call, hey, x, y is equal. I'm going to call that function. It's called mesh grid based on my x's and y's. And then I'm going to print my x and print my y. Let me now, I'm going to turn off printing x and y. This was just a check. So I can see that my matrix X has repeated rows of all of the y's that I have. And my matrix Y has repeated columns of all of the y's that I have. And when I combine the two, so I take -2, -2, -1, -2, 0, -2, 1, -2, 2, -2, I get all of those points that I was walking down, right? And now I just have to go and compute Z. What did I want to do? Z of x, y. I'm going to copy this, though I'll have to change how I do squares. So maybe it works, maybe it doesn't. It does. So it's -6 times NP. Just give me 2 minutes to compute this, and then we will plot it. We'll be ready for plotting next time. So I will take now these matrices x and y that has corresponding x and y's of all of the points that I want to compute for. I'm going to create Z that has pretty much the same dimensions. Yes, there is minus here, here. So minus, this is e to the minus x squared minus y squared. And when I print Z, oh, what else? Doesn't like the indent.
Yeah, mine is not.
So now I actually have z that is of the same size as that x and y, and I have computed z for every xy pair. So this mesh grid creates me those matrices that I need of locations on the grid. And then Z just computes using those matrices, and I'm ready to plot. I have the data. I still don't know how the data looks good because I need to plot it to do that. But I have all of the data. So I have X, Y, Z for every location on that graph. Did everybody catch this? All right, we're going to be plotting on Friday.